Okay, so today we're going to be looking at some real-world applications of logarithms. Not too much more I can say about that. I think that's pretty self-explanatory. Let's get going. So in terms of today's plan, we're going to be finishing off Chapter 8 today just by looking at some real-world applications of logarithms. And since they're a connected concept, we're also going to be looking at applications of exponential functions. It's going to kind of tie in together all in one today. We'll need to use the tools we've learned in previous lessons in this unit in order to tackle these today. It's really going to take a lot of the things that we've learned and just kind of throw it all together. The first thing we're going to do today, though, it's going to be a bit of a different approach. We're going to look at, but not actually attempt, a diploma exam question involving a real-world application of logarithms. Now, we will come back to it a little later on, of course, but I just want us to have a look just to see what we're up against with this. I have a strategy that helps you solve these. It'll be pretty simple, I think, but we'll get to that when we get to that. So then after we look at that, though, we'll learn how to approach a wide range of real-world applications. And then, like I mentioned at the end of the lesson, we'll complete that diploma question just to get it out of the way. It's all going to come full circle. You'll see what I mean. Anyway, let's get going. So just as I said, we're going to start with this diploma question. Just out of curiosity, by the way, you can see up at the top, 33% of students in Alberta got this question right when it was put on this diploma exam. And I think the main reason for it is they give you this formula here. The technique I'm going to show you today actually ignores this formula altogether. I'll be honest, this formula even just puts me through a bit of a loop. I don't really like what they're doing with this one because their definition of intensity is just miserable. But there's another way to approach this that we'll get into a little later on. If you want to pause the video here and actually give it a good read and think about it, you're more than welcome to. But aside from that, we're going to move on. We'll come back to this one later on. So logarithms in the real world. There are three common applications of logarithmic scales. There's others than this, of course, but just three that you'll see more often in this course. The Richter scale, which measures the magnitude of earthquakes. The pH scale, which measures how acidic or basic a chemical is. You can remember that from Science 9 or chemistry if you've taken it. And then the Bell scale, which actually measures the loudness of a sound. Now, typically we don't use bells, we use decibels, which are 1/10 of a bell. Same idea though. Now, these scales are logarithmic, which means that a difference of 1 on each scale corresponds to a factor of 10 difference in intensity. So in other words, if you go up, like this is a pH scale, this whole rainbow looking thing right here, if you go up by 1 pH, you're losing 10 times as much concentration of hydrogen ions in your solution, right? Same with the Richter scale. If you have a magnitude 3 earthquake versus a magnitude 4 earthquake, that magnitude 4 earthquake is 10 times more intense. That's what we would deal with logarithmic scale. Anyway, so for some examples here, an earthquake, once again, with a magnitude of 8 is blank times as intense as a magnitude of 7. Well, since that's just one difference on this scale, that's a difference of 10 times more intense, right? So the magnitude of 8, 10 times more intense than the magnitude of 7. What about an earthquake with a magnitude of 5? How does that compare to an earthquake with a magnitude of 2? Well, let's put it this way. From 2 to 3, that would be 10 times difference. 3 to 4 is another 10 times. And then 4 to 5 is yet another 10 times. But 10 times 10 times 10, well, that would be 1,000 times as intense, right? So they all kind of cascade onto each other, right? Next one, a pH of 3 is blank times as acidic as a pH of 7. Just a reminder with pH, the lower your pH number, the more acidic you are. So that isn't backwards or anything. That is written correctly. Anyway, if we follow this back, 7 to 6 would be 10. And then 6 to 5 would be 100. 5 to 4 would be 1,000. And therefore 4 to 3, we're at 10,000, right? So I just added a 0 for each one of the differences. I was counting back from 7 to 3. That was what I was just doing there. So 10,000 would be the answer there. pH of 3 is 10,000 times as acidic as a pH of 7. The last one here, a power saw, which is 120 decibels or 12 bells if you prefer, because remember 10 decibels is 1 bell, is blank times as loud as leaf rustling, which is only 10 decibels, or in other words, 1 bell. Now, decibels, of course, that's used for communicating, but in terms of actually doing calculations, I'd recommend you ignore it. Look at the difference between 12 bells and 1 bell. If we were to count backwards there, watch this. So 12, maybe I'll go the other way. So it's talking about how much louder it is. Let's start at 1. We'll go 1 to 2 is 10 times more intense. 2 to 3, we're at 100. And then to 4, and then 5, and then 6, 7, 8, 9, 10, 11, 12. Ooh, that number right there. So if I break this apart, We're interesting to see that's 100 billion times as loud as a leaf rustling. Wouldn't seem like that, like it's kind of hard to quantify that, but the math checks out here, right? Another way you could have thought of that is 12 minus 1. The difference between that is 11. Notice how many zeros there are in this number. If you count the zeros up, they'd be 11 zeros. We'll use that actually. So once again, 100 billion times as loud as a leaf rustling. Again, sounds mind-blowing, but it checks out, believe me. Anyway, so difference in intensity. With those past examples, it wasn't too tough to find the difference in intensity because they were all a whole number apart on the scale. So in other words, if you notice, like just going back here, 8 to 7, that's a whole number apart. It's just one apart. 5 to 2, whole number apart. There was a 3 difference, right? You get the idea. But what if the difference isn't a whole number? So for example, how do we compare the magnitude 6.5 earthquake with a magnitude 4.4 earthquake? You know, that's going to be like 2.1 difference there. That's not a whole number. We can't just like add, 2.1 zeros onto something. It doesn't make sense like that, right? Well, here's the easiest way to do this. And I was alluding earlier when we looked at that diploma question. This is usually my go-to strategy, no matter what kind of question I'm dealing with an application of a logarithm. This is how I go about it. Step 1, find the difference in the magnitudes, or the pHs or the loudnesses, whatever you got. I'll just call them magnitudes for now. So find the difference. Difference means subtraction. So in this case, it'd be 6.5 minus 4.4. That's a difference of 2.1. All right, so I find that first. Step 2, this is our last step. It's just that quick already. Raise 10 to the power of that difference. So in other words, 10, in this case, to the power of 2.1. Now, I don't know what that is off the top of my head. You're going to have to use a calculator for that. So 10 to the power of 2.1. I'm just going to round to the nearest whole number. It's about 126 times more intense. So we knew if it had a difference of 2, like 6.5 to 4.5, that's a difference of 2. Well, that would be 10 times 10, so 100 times different. 2.1 adds quite a bit more, right? So it's 126 times more intense. And that's how we deal with it, right? So step 1, find the difference. Step 2, raise 10 to the power of that difference. Oh, look at that. We already did it. Next question here already. So that work I just did, I totally forgot that I threw that in there. Magnitude 6.5, magnitude 4.4. You know what? Forget it. I'll just do it one more time. 6.5 minus 4.4 equals 2.1. 10 to the power of that. So 10 to the power of 2.1. That gave us roughly 126 times, right? It's 126 times more intense. That's all. What about this one? How many times more acidic is milk, which has a pH of 6.6, than laundry detergent, which has a pH of 11.8? Remember, acidic is lower on the pH scale, so the question still makes sense. So we're looking at how many times more acidic it is. Just take the difference between those two numbers. So we'll go 11.8 minus 6.6. Just typing that in just so I don't get mental math wrong here. It's 5.2. There we go. And then raise 10 to the power of that. So 10 to the power of 5.2. Throw that in your calculator as well. Give me a second. 10 to the power of 5.2, just rounded to the nearest whole number, is 158,489. There it is, right? Super quick, super clean, super simple, right? Just find the difference between your intent or your magnitudes and then go 10 to the power of that difference. That gives you your difference in intensity. So 158,489 times more acidic. Neat, right? Moving on. What about this one? How many times louder is a train whistle, which is 90 decibels? That actually sounds too low. A train whistle only being 90 decibels, because that power saw earlier was 120. You'd think it'd be louder than that. But anyway, I won't argue with it. Let's say train whistle, 90 decibels, then a piano, which is 65 decibels. And just remember, the bell is the base unit here. One bell is 10 decibels. So to go about doing this, anytime I see decibels, I'm going to change this into bells right away. So one bell is 10 decibels. So 90 decibels, that's 9 bells. 65 decibels, well, that'd be 6.5 bells, right? Decibels are better for communicating. That's just what we use. But bells are the actual real unit, and that's what we need to use here. Anyway, so strategy here, as always, to find how much more loud that is, just find the difference. So 9 minus 6.5, that is, of course, 2.5. And then just go 10 to the power of that. So 10 to the power of 2.5, that is going to equal, just to the nearest whole number, 316 times. So according to this question, a train whistle is 316 times louder than a piano. But in all honesty, I think that's way too low. I think a train whistle is probably more than 130 decibels. It's very loud. But anyway, I'm not going to argue with this. All right, so this question is going to stir things up a little bit. We're going to move kind of backwards here. So in this question, we say an earthquake with a magnitude of 7.5 is 500 times as intense as the smaller aftershock. What is the magnitude of the aftershock? Well, in previous questions, we would take the difference between your magnitudes. So 7.5 minus the magnitude of the aftershock, that would give us what we raised to a power to get to 500. In this case, we're just going to have to work backwards. Bear with me on this. Here's how my brain works with this one. 500 is like, that's the difference in intensity. That's how many times more intense it is, right? So I know 10 to the power of something, I'm just going to call it x, 10 to the power of x equals 500, right? Now that x represents the difference between our magnitudes, right? So usually we would go 7.5 minus whatever, and then go 10 to the power of whatever that was, and that would give us our 500. But we have to work backwards here. So just keep in mind, x is going to represent our difference in this case. Now, if only there was some way we could solve for x here. Like, are we going to have to guess and check this? I'm just kidding. Of course, we're not going to have to guess and check this. This is an exponential function where x is the unknown up in the power there. We can just use logarithms to solve this, just as we've been doing earlier in this unit. To do logarithms here, just do the old switcheroo. The base becomes the base of the log. So this is going to be log base 10. You don't even have to write base 10 because if you just write log, you'll assume that, but I'll be kind here. I'll write log base 10. The answer is what goes into the log. So 500 goes into the log. And then the answer of the log is the thing that was your old exponent. So that's going to equal x. Type that in your calculator real quick. Log base 10 of 500. You just press log of 500 because remember, just basic log is log 10. What I got for x when I did that, I got x equals, you know what, I'll just take the 2 decimal places. That's actually going to round up to 2.70. Now remember what I said earlier, x represents the difference. So in other words, 7.5 minus something equals 2.70. Maybe I'll write that out. 7.5 minus something equals 2.70. Well, to find this, of course, we just need to add the something on both sides. There it is, plus something, and then subtract away your 2.70. Long story short, 7.5 minus 2.70. This is going to give us our unknown equals 4.8. That right there, that 4.8, that is the magnitude of your aftershock, right? If you don't believe me, you can always work backwards. Find the difference between those two and then go 10 to the power of that difference. You're going to get something pretty darn close to 500, right? We rounded here, so it won't be perfect, but it'll be pretty darn close. Whew. Anyway, let's keep rolling. Next example here. Vinegar with a pH of 3 is 245 times more acidic than coffee. What is the pH of coffee? Okay, so since vinegar is more acidic, and pH is kind of backwards, where a lower pH is a more acidic pH, we know that the pH of coffee is going to be some number bigger than 3, right? So in other words, it's going to be something greater than 3, right? Just keep that in the back of your mind. Otherwise, this question is done the exact same way as the other one. Let's take that difference in intensity, like how many times greater it is, and let's make that equal to 10 to the power of x. So 10 to the power of x, so this x representing once again your difference, 10 to the power of x equals 245. Well, just like before, we need to use logarithms to solve this. So log, base of the log is going to be the base of the exponent here. So log base 10 of the answer goes into the log. So of 245 equals our x. Give me a second here. Log base 10 of 245. That's going to give me, I'll just round to 2 decimal places again. X equals 2.39. So 2.39. That's our difference. Now, remember, our answer is going to be for coffee. Coffee is, you know, we already were told vinegar is more acidic than coffee. So coffee has to have a bigger than 3 pH. So let's put it this way. Let's call question mark the pH of coffee. The pH of coffee is question mark minus the pH of vinegar. So minus 3 equals 2.39, right? We just have to add 3 on both sides. That's all we got to do here. So question mark the pH of coffee equals 5.39. It doesn't say what to round to. So you know what? 2 decimal places is great. You could have done just 1 if you wanted to, like 5.4 would have worked just fine. Whatever you do, though, that is going to be the pH of coffee. And again, if you don't believe me, you can always work backwards, right? 5.39 minus 3, that'll give you 2.39. 10 to the power of 2.39 is 245. We know how many times more intense it is. You just have to know with pH, the scale, again, is backwards. The lower the pH, the more acidic that liquid is. That's basically all we're looking at. All right, here's another one. Once again with a power saw. I don't know what the interest is with power saws in this is, but it is what it is. So a power saw, which is 12 bells, is 1/5 as intense in loudness as a rock concert. What is the loudness of a rock concert? Okay, so this one's kind of like the last one. Notice it's 1/5 as intense. That tells us it's going to be like the power saw is going to be a lower number than the rock concert. So the rock concert is going to be greater than 12 bells. That might be important to note. However, notice how small this this number is here, right? 1/5 as intense. What I would almost assume, since we're going to have a 1/5 here as our difference in intensity, I'm going to actually assume that we're doing this a bit backwards, and we're going to go the power saw minus the bigger number. Notice in all the other previous questions we did, we always went like the bigger number minus the smaller number, but that gave us a number that was, relatively large. This number here is just 1/5. If you don't believe me on this one, watch what's going to happen. Just from the previous questions here, we're going to go 10 to the power of x equals our magnitude or our intensity difference here. So our intensity difference is 1/5. Also, just like previous questions we've done here, we're going to change this into a log. So log base 10 of our answer, which is 1/5, equals x. If you throw that in your calculator, log of 1/5, you're actually going to get a very strange number for x. You're going to get x equals negative 0. Again, rounding just to 2 decimal places, negative 0.70. Very strange number there, like really, really, really strange number there. It's so weird to have a negative as our difference, right? Because that's what x is. Remember, x is our difference. The only way we can have a negative difference is if the smaller number was written first. Like, for example, if you had like 4 minus 7, that'll give you -3, right? The only way, I don't know what's with my threes lately. That's a -3, right? There we go. Geez Louise. Anyway, so 4 minus 7 is -3. The only way you're going to get a negative difference is if you had a smaller initial number. Well, we know the power saw is not quite as loud as a rock concert. We know the rock concert has to be greater than 12 bells. The long story short, when I write this up now, I'm going to say this is 12 minus something, smaller number minus bigger number, equals -0.70. That's about as tricky as they get. They really try to slip you up with that sometimes. Just be mindful of what it means to have a negative difference. You have to have your smaller number first. It's just a logic thing, right? Anyway, so since we're looking for this, we're trying to find the question mark. I think the easiest way to do this would be to add the question mark on both sides. And then to get rid of -0.70, I'd have to add that on both sides. Long story short, you're going to get question mark equals 12.7 bells. That would be the loudness of the rock concert, right? So the rock concert has a higher loudness than the power saw. Not a big surprise, right? Anyway, moving on. I think we're almost done, actually, if it's going to let me move on. There we go. There we go. All right. So here's a chemistry example. The pH of a solution is defined as pH equals -log H positive. So it's pretty weird. So what we're doing here is we're comparing the pH to its actual component, the thing that actually makes a pH, right? So H positive is the hydrogen ion concentration expressed in moles per liter. If you've not taken chemistry, don't sweat this too much. Just try to look beyond what it's asking and just try to calculate the numbers. I'm not going to require you, of course, to know any chemistry in this. So let's say a chemical has a pH of 5.7, right? So we know the pH 5.7. What is the hydrogen ion concentration? There's no tricks on this one. We're not dealing with intensity differences. We don't have to use that whole difference and then take it to the power of that thing. We can just throw this right in. So we can say 5.7 equals -log of H positive. Now, we like to, of course, if we have to solve a log, we have to solve what's inside the log. We'd like to turn this into an exponential function, but we have to get the logarithm by itself first. So I'm going to move the negative to the other side. -5.7 equals +log of H plus. Now, if I'm going to turn this into an exponential function, start with your base. Because it didn't list a base here, we have to assume it's 10. So base to the power of the answer, so to the power of -5.7, equals the thing that was in the log, so H positive. And boom, there it is right there. You can just throw that straight in your calculator. 10 to the power of -5.7. It's going to give you kind of a gross number here. H positive equals, we'll just say to, I was going to say to 2 decimal places, but what's funny here is either way, it's going to round right up. This is going to round right up to 2.0. And then it says E -6. That just means times 10 to the -6. Oh, and then the units, of course, moles per liter. the question gives you units, try to respect that. That's all I got to say, right? Next one, if a different chemical has a hydrogen ion concentration of 3.4 times 10 to the 4 moles per liter, what is its pH? Oh, interesting. That's quite a high concentration there. Well, let's find out. So if a different chemical has a hydrogen ion concentration of that, let's see, we just have to throw that in there. So pH equals negative log of that hydrogen ion concentration, which is 3.4 times 10 to the 4. Just throw that straight in your calculator. Negative log 3.4 times 10 to the 4. It's probably going to give us a really low pH. Yeah, really low pH. So this is kind of a broken question. I don't like this one at all. The pH of this, following this formula, and this is serious, we didn't do anything math wrong here, is negative 4.5. Wow, that's like a hyper pH right there. That's insane. This question, actually, this probably is actually a typo. What if it's 10 to the negative 4? Maybe we'll even just try that, just so we get something a little more reasonable here. For those of you who've taken chemistry, you know pH is usually just between 0 and 14. Having a negative pH, that'd be pretty wild, right? Let's try something else in this one. Let's make that 10 to the negative 4. That might be just a typo here. So pH equals negative log of 3.4 times 10 to the negative 4. Let's do that one a little bit better. I think I'm going to correct that for future years because that definitely is going to make that a little bit better. Anyway, typing that in my calculator now. Oh yeah, much better. We'll just do it to 2 decimal places. pH equals 3. That'll round up to 3.5. So 3.5 would be our pH there. That's a little bit more comfortable than having a negative pH. Yeah, I apologize about that. You know what? I'll own up to that. I'll make sure I change that in our note packages going forward. So 2022, you guys are the last group to ever have seen something that garbage. But anyway, moving on. Believe it or not, we're not quite done yet. We have a little bit more that we have to cover here. Growth and decay problems are a really, really big application of this. Now, it's more an application with exponential functions, of course, but believe me, this is also something that comes around with logarithms as well. So another real world application is how things grow or decay over time. So a couple examples of this would be population growth. That can be exponential, especially if it's of like a virus or something. Radioactive decay of certain elements is exponential. So that would be something you'd see in physics 30. There is a formula on our formula sheet, lucky you guys, that actually helps us with this. Straight from your formula sheet, it says y equals a times b to the power of t over p. It is unfortunately your job to understand what each of these letters mean. But if we break it down from what we know, it shouldn't be too terribly bad. Y is your final amount or population. A is your starting amount, right? When we were first learning about exponential functions at the start of this chapter, I do believe we were talking about how A in an exponential function is your y-intercept. That's your starting amount, right? B is your growth or decay rate as a decimal or as a fraction. Remember, if B is bigger than 1, you're growing. If B is between 0 and 1, you're decaying, right? T is the elapsed time, so it's how much time has passed since this growth or decay thing was watched. And then P is the time period, which is one of the fancier things here. That's just how long it takes for it to grow or decay by the rate B. So if I told you, oh, it doubles, so B would be 2. If it doubles every 5 years, well, then P is 5 years. So it'd be, P would be the denominator, the exponent there. Anyway, let's see an example. Hitting out the big guns here first. We're going to look at a physics 30 half-life question. The half-life of plutonium-241 is 14.4 years. Suppose you currently have a 20.0 kilogram sample of plutonium-241. How much will remain in 100 years? In case you're not aware with half-life, half-life just means we're multiplying by 1/2, in this case, every 14.4 years. Let's set this up. Y equals a times b to the power of t over p. That's our formula. We want to find how much will remain. That's going to be our y. Equals, figure out how much you were starting with. That's your a value. You currently have 20.0 kilograms, so I'm just going to say 20. The half-life, that means we're multiplying by half each time, so that's going to be our b value. I like using 0.5. You can use literally 1/2. I'm going to fix that 0.5 though. There we go. You can literally use 1/2 if you want, but I prefer the decimal. It's just a matter of preference. To the power of t over p. Well, t is the elapsed time. We were told this is going to go for 100 years, so 100 over p is the time period. That's how long it takes to be cut in half. Well, that'd be 14.4. Just a matter of throwing that in your calculator at this point. I could have made this question a lot harder and told you how much was left and told you to find how many years we're passing. But you know what? I guess I was nice to you. So anyway, throw that in your calculator. 20 times 0.5 to the power of this, really, you'll want to put that in brackets when you put it in your calculator, of course, to the power of 100 divided by 14.4. This is going to give us y equals 0.16. And that, yeah, that's not a typo. That is correct. 0.16 kilograms. You're not going to have very much plutonium-241 left over after 100 years, right? So most of it's gone at that point. After 14.4 years, you'd only have 10 kilograms left. After another 14.4 years, you only have 5 kilograms left. After a full 100 years pass, you don't have all that much left, right? It's all gone away, right? Now, grand finale here. Like I said, everything's coming full circle, and I'm going to prove it to you here. I want you guys to give this question a try. This is the same one we looked at the start. Again, 33% correct rate. I want you to use what we've talked about today. At the very beginning of the lesson, when I showed you this, I say the formula they give to you here, pretty much baloney. There is a way you can use it. I just don't really see it as being a very easy way at all. So I'll just read the actual question part to you. You'll want to read the box up here too, especially this, the fact that it's 127 decibels. If the intensity of the sound of a vuvuzela is 5,000 times greater than the intensity of the sound of a lawnmower, then the measured loudness of the lawnmower to the nearest decibel is what? Pause the video here. I want you to give this one an honest shot. All right, so I'm hoping you actually give this an honest shot. Let's see if you were able to get this one right. If you have a really good intuitive understanding of how the decibel system works, you could actually just guess and check this one and you'd be just fine. Some actual reason could actually solve you through this. But in other diplomas, I've seen they've been a little bit more sneaky with this. So we do need to know the proper way. Remember, the rule is we want to find the difference between our loudnesses. That is what we take to a power to give us our difference in intensity as like a times factor. We were given that times factor at the end here. It's 5,000 times greater. We're going to have to start there and work backwards like we did on those later examples. 10 to the power of something equals 5,000. That something represents our difference. That's the difference between our loudnesses in I guess it would be in bells. Remember, that'd be 12.7 bells instead. So to find that x, we just need to turn this into a logarithm. Log base 10, because we had the base of the exponent was 10, of our answer, which is 5,000, equals x. Throw that in your calculator. Log base 10 of 5,000. That gives me roughly 3.7. So x is 3.70. Okay, hopefully you're with me so far. Remember, that number there, 3.70, that represents our difference. The vuvuzela at 12.7 bells, like forget decibels, always turn it to bells. 12.7 bells is going to be the bigger number here. So we're going to have 12.7 minus the lawnmower, I'll just call it question mark, equals 3.70. To solve for the question mark, just a bit of basic algebra. Add the question mark over, subtract 3.7. Bingo, bango, bongo. You're going to get question mark equals 9, and that's bells. Back to decibels though, right? So 9 bells is great for doing our math. For actual communication, we use decibels to express loudness. That's 90 decibels. Boom. You got that? You're already ahead of, I guess, 67% of Albertans. Holy smokes, right? Again, I think the reason why this question had such a low success rate is mostly because this formula always throws people through a loop. Anytime you see difference in intensities, like 5,000 times greater or whatever, I don't bother with this. If you want to snoop around with it and see if you can figure out a way to make some sense out of it, you're more than welcome to. Personally, like it doesn't define these very well to me. Measured intensity versus reference intensity, we weren't even given all that many numbers. I don't really see much use in this formula personally, but that's just my opinion. Anyway, for practice, here's some practice questions. Very wise idea to give these a shot. If you need any help, please let me know.